In the endless stillness of space, light travels for billions of years before reaching us. And sometimes that light carries secrets, whispers from a universe so young, so distant, that it almost feels like a dream. Tonight, we set our gaze upon one of those whispers, a galaxy named MoM-z14. Not just any galaxy, but the farthest one humanity has ever seen. Its name might sound like a string of code, but behind it lies one of the most astonishing cosmic revelations of our time. MoM-z14 is not merely far away in space, it's far away in time. The light we now detect from it began its journey over 13.5 billion years ago, when the universe was just a tiny fraction of its current age. To see it is to look into a time when galaxies were just beginning to form, when the first stars ignited the darkness. This is not a journey through space, it's a journey into the past. But how do we even find something so impossibly remote? How can a speck of ancient light survive eons of cosmic expansion to be caught by our eyes? The answers lie in the quiet work of instruments like the James Webb Space Telescope, which peers deeper into the cosmos than anything before it. In this audio voyage, we'll explore the wonders surrounding MoM-z14, what it is, how it was discovered, and what it tells us about the earliest days of our universe. We'll delve into cosmic redshifts, the formation of the first stars, and what it means to detect something from an age before galaxies were common. MoM-z14 is not just far, it is ancient. It is fragile, and it is real. So as you settle in and allow your mind to drift with the stars, imagine what it means to observe the earliest flicker of creation, a beacon from the other side of time itself. Let's begin our journey to meet MoM-z14, the most distant galaxy ever found.
Chapter 1. What is a galaxy, and how do they form? In the vastness of the cosmos, galaxies are the great cities of the universe, immense, luminous islands of stars, gas, dust, and dark matter, drifting through an expanding ocean of space. Each one is home to billions, sometimes even trillions of stars. Some are small and irregular, others spiral with graceful arms, and some are massive and elliptical, like ancient relics of a time long past. But what exactly is a galaxy, and how does such a magnificent structure come into being? To understand galaxies, we have to begin at the beginning, not of galaxies, but of everything. Around 13.8 billion years ago, the universe was born in a violent and brilliant event we call the Big Bang. In its first few 100,000 years, the cosmos was a searing hot soup of particles, light, and energy. It was a place without structure, without stars, and certainly without galaxies. Then something began to change. As the universe expanded, it cooled. And eventually, about 380,000 years after the Big Bang, the first atoms formed, mostly hydrogen and helium. This moment, known as recombination, allowed light to travel freely through space for the first time. That ancient light is what we now detect as the cosmic microwave background, a faint glow that bathes the universe and tells us of its earliest state. But the universe still had no galaxies. It was dark, quiet, and filled with a nearly uniform distribution of gas. The seeds of structure, however, had already been planted. Tiny fluctuations in the density of matter, random, minute wrinkles in the early universe, acted as gravitational attractors. Over millions of years, these slightly denser regions began to pull in more gas through the invisible force of gravity. As more matter accumulated, the pressure and heat in the centers of these clouds increased until something truly magical happened. The first stars were born. These were not ordinary stars. They were giants, possibly hundreds of times more massive than our sun. They burned bright and died young, exploding in cataclysmic supernovae that enriched the surrounding gas with heavier elements. This process helped shape the environments that would lead to the formation of future generations of stars. As more stars formed, their mutual gravity pulled them into larger groups. These early collections of stars, bound together by their own gravitational pull, became the first proto-galaxies. Over time, proto-galaxies merged with one another, growing larger and more complex with each collision. This hierarchical merging, small pieces joining to form larger wholes, is one of the dominant processes in cosmic evolution. Galaxies are not static islands. They are dynamic, ever-changing systems, shaped by the interactions they have with their surroundings and with each other. But stars and gas alone do not make a galaxy. There's another essential ingredient, an invisible one: dark matter. Though we cannot see it, dark matter makes up the majority of the mass in most galaxies. It does not emit or absorb light, but its gravitational influence is unmistakable. Without dark matter, galaxies could not hold themselves together. The rotation of stars within galaxies would fling them apart if not for the gravitational glue of dark matter halos. These halos provide the scaffolding upon which galaxies form and evolve. In this delicate interplay between light and shadow, between visible matter and the unseen, galaxies emerge as masterpieces of cosmic design. Over billions of years, the universe has given rise to hundreds of billions of galaxies, each unique, each a theater of cosmic drama. Some are calm and orderly, forming stars in quiet spiral arms. Others are violent and chaotic, crashing into neighbors and awakening the supermassive black holes at their centers. Galaxies also evolve. Young galaxies tend to be irregular, clumpy, and full of gas. As they grow older and undergo collisions, they often settle into more stable shapes. Spirals flatten out, ellipticals puff up, and some galaxies even lose their ability to form new stars altogether. So when we look at a galaxy like MoM-z14, we are not just observing a distant light source. We are witnessing a moment in the life of the universe itself. A glimpse into an era when galaxies were only beginning to exist, when the first attempts at cosmic architecture were being drawn across the night. MoM-z14, so faint and so far, is likely a compact, primitive galaxy. It may lack the majestic arms of a spiral or the immense scale of an elliptical, but its simplicity is what makes it so profound. It is a message from a time before complexity, a message from when the universe was young, uncertain, and just learning to build. And in understanding what a galaxy is, how it is born from darkness, shaped by gravity, enriched by stars, and held together by the unseen, we begin to see the significance of finding one so ancient, so far away. Because to see MoM-z14 is to touch the very beginning of this grand cosmic process. It is to understand not just where galaxies come from, but where we come from. For everything we are, every atom in our bodies, every element that sustains life was forged in the hearts of stars within galaxies like these. We are, in every sense, the children of galaxies, and MoM-z14 is one of our oldest ancestors.
Chapter 2. What does far away really mean in the universe? When we speak of distance in everyday life, it's usually something we can imagine. Steps down a hallway, miles across a city, hours across a country. But when we turn our eyes to the universe, far away becomes something almost unfathomable. It stretches beyond the scales of time, reason, and imagination. So, what does far away really mean when it comes to a galaxy like MoM-z14? Let's begin with the basics. Light, the fastest thing in the known universe, travels at approximately 300,000 kilometers per second. That's fast enough to circle Earth more than 7 times in a single second. Yet even at that incredible speed, it takes light over 8 minutes just to travel from the Sun to Earth. The nearest star beyond our Sun? Over 4 years away, even for light. That's where we get the term light year. The distance light travels in 1 year, which is nearly 9.5 trillion kilometers. So when we say that MoM-z14 is over 13.5 billion light-years away, we're saying that the light we're seeing today left that galaxy more than 13.5 billion years ago. That's not just distance, it's time. Looking at MoM-z14 is like opening a time capsule sealed when the universe was still in its infancy. But here's where things get more complex. Because the universe is not static, it's expanding. And the farther away an object is, the faster it appears to be receding from us due to this expansion. This means that while the light from MoM-z14 took 13.5 billion years to reach us, the galaxy itself is now much farther away than that. In fact, based on current models of cosmic expansion, MoM-z14's present distance from us could be more than 30 billion light-years. Yes, you heard that right. The light is 13.5 billion years old, but the galaxy itself may now lie over 30 billion light-years away, thanks to the stretching of space. This strange reality is made possible by the universe's continuous expansion. Imagine a balloon being inflated, with dots drawn on its surface. As the balloon grows, the dots move farther apart, not because they are traveling across the surface, but because the surface itself is stretching. Space behaves in a similar way. So when we look deep into the cosmos, we're not just looking across distance, we're looking back in time, across an ever-expanding landscape. This is where the concept of look-back time comes in. Look-back time is the time it has taken for the light of a distant object to reach us. When we observe MoM-z14, we're not seeing it as it is now, we're seeing it as it was more than 13.5 billion years ago. The universe was less than 300 million years old. Galaxies were just beginning to form, stars were freshly born, the cosmic stage was just being set. There's another important idea we need to understand: redshift. As the universe expands, the light from distant galaxies becomes stretched, its wavelength elongated, shifting it toward the red end of the spectrum. And the farther away a galaxy is, the greater its redshift. That's why we describe MoM-z14 as having a redshift of z equals 14. This number tells us just how much the universe has stretched since that light began its journey. To put it in perspective, a redshift of z equals 1 means the universe has doubled in size since the light was emitted. At z equals 2, it's tripled. At z equals 14, the universe has expanded more than 15-fold. It's like receiving a message in a bottle that has been floating not just across an ocean, but across a sea of time, one that has grown wider and deeper as the message drifted towards us. These extreme distances aren't just impressive, they're fundamental to how we understand the universe. They let us see the evolution of cosmic structures. By observing galaxies at various distances, and therefore at various points in time, we build a kind of time lapse of the universe itself. Nearby galaxies show us what the cosmos looks like today. Galaxies farther away show us what it looked like billions of years ago. And MoM-z14 shows us what the universe looked like just after it began. It's one of the earliest pieces in the great cosmic puzzle. And yet, even now, as we gaze upon its ancient light, we must accept a strange truth. We may never know what MoM-z14 looks like today. It is too far, too distant in time and space. Any changes it has undergone since then are hidden from us, perhaps forever. It's a reminder that the cosmos we see is not the cosmos as it is, it's the cosmos as it was. The night sky is not just a window to space, it's a record of time. So, what does far away mean in the universe? It means stepping outside the bounds of the familiar. It means looking at light that began its journey before Earth existed. It means reaching across billions of years to touch the infant universe. When we speak of MoM-z14 as the most distant galaxy ever discovered, we're not just measuring distance, we're measuring memory. The memory of a cosmos awakening from its darkness, a flash of light from a newborn galaxy, stretching through an expanding void until it finally arrives here, to us. To see it is to witness the dawn of everything.
Chapter 3. The telescope that discovered MoM-z14. To find something as distant and ancient as MoM-z14, we needed a new kind of eye, an instrument not limited by the boundaries of ordinary sight, but one capable of capturing the faintest whispers of the early universe. That eye is the James Webb Space Telescope. Launched in December 2021, the James Webb Space Telescope, often called JWST, was designed to go beyond what any previous telescope could achieve. Built as a successor to the legendary Hubble, Webb is not merely a telescope. It is a time machine, a precision-crafted instrument with one singular mission: to see farther back in time than humanity ever has before. But what makes it so powerful? Why was this the telescope that found MoM-z14? The secret lies in its ability to see infrared light. You see, as the universe expands, the light from distant galaxies becomes stretched. What might have begun as ultraviolet or visible light billions of years ago has now shifted deep into the infrared part of the spectrum. This redshift makes ancient galaxies invisible to most telescopes, but not to Webb. JWST was specifically designed to detect the stretched infrared light. Its massive gold-coated mirror, over 6.5 meters wide, collects even the faintest signals from the earliest stars and galaxies. These signals are so weak, so fragile, that they would be drowned out by heat if not for Webb's unique design. That's why the telescope operates in deep space, far from Earth's warmth and light. It orbits the Sun at a special location called the Second Lagrange Point, or L2, about 1.5 million kilometers from Earth. There, it stays cold and still, its instruments shielded by a tennis court-sized sun shield that keeps it at cryogenic temperatures. Everything about Webb was designed to be exquisitely sensitive. Its instruments, NIR-CAM, NER-SPEC, MIRI, and others work together to peer into dusty star-forming regions, icy moons, and most importantly, the most distant galaxies ever formed. When astronomers trained JWST on a small patch of sky, dark, unremarkable, and seemingly empty, they didn't expect to see much. But what they found was breathtaking. The deep field images captured by Webb revealed a cosmic forest of ancient galaxies. Some of them were so distant, so redshifted, that they seemed to exist impossibly early in the universe's timeline. One of them stood out, a compact, bright dot with a redshift of Z=14. A galaxy whose light had traveled over 13.5 billion years to reach us. That galaxy was MoM-z14. It wasn't just the most distant galaxy ever found. It was a challenge to everything we thought we knew. How could such a well-formed galaxy exist so early? How had stars gathered, ignited, and formed into a structure in so little time? These questions are still being debated. MoM-z14 and other ultra-distant galaxies are forcing astronomers to rethink parts of our cosmic models. And all of it, every discovery, every question, was made possible because of the James Webb Space Telescope. This telescope doesn't just take pretty pictures. It shifts paradigms. It rewrites textbooks. It forces us to reconsider what we thought was possible in the early universe. With each deep gaze into space, it stretches the boundary between the known and the unknown. Webb's mission is far from over. In fact, it has only just begun. MoM-z14 is likely the first of many such discoveries. Galaxies older, fainter, and farther than we've ever imagined may still be waiting, hidden in the cold light of infrared. And thanks to this extraordinary instrument, we now have the tools to find them. So when you look at an image captured by JWST, remember, you're not just looking at stars and galaxies. You're looking at history. You're looking at light that began its journey before there were planets, before there were oceans, before there was life. You're looking at the first chapters of a story still being written. And MoM-z14? It's a whisper from page 1.
Chapter 4. What does redshift z=14 mean? In the language of the universe, distance is not measured only in kilometers or light years. It's also measured in how much light has shifted during its journey across expanding space. This shift is called redshift, and it holds the key to understanding just how far and how old a galaxy like MoM-z14 truly is. Let's begin with the basics. Light travels through space in waves, like ripples across a cosmic ocean. The distance between those waves is called a wavelength. Light with shorter wavelengths appears blue or violet. Longer wavelengths appear red or infrared. But as light travels through the stretching fabric of space, those wavelengths get pulled apart. They become longer, redder. This stretching is what we call cosmological redshift. It doesn't happen because the object is moving through space. It happens because space itself is expanding. The light waves are not simply passing through empty nothingness. They're embedded in a fabric that's growing, pulling them farther apart. The result? Light that began in the ultraviolet or visible range emitted billions of years ago arrives at Earth stretched far into the infrared. And that's where redshift comes in. Astronomers use a number, z, to describe how much the light has been stretched. A redshift of z=1 means the universe has doubled in size since the light was emitted. At z=5, the universe has grown 6 times larger. But MoM-z14? Its redshift is z=14. That means the universe has expanded more than 15 times since the moment that galaxy's light first began its journey. That single number 14 tells us more than distance. It tells us time. A redshift of 14 places MoM-z14 at a point just 290 million years after the Big Bang. That's only 2% of the universe's current age. Everything was different then. There were no spiral galaxies, no mature stars. The cosmos was still emerging from the long night after the Big Bang, a time astronomers call the cosmic dark ages. But how do scientists calculate redshift? They look at the spectra of galaxies, the breakdown of their light into its component colors. Much like a prism splits sunlight into a rainbow, astronomers use instruments to spread out the light from distant galaxies. Within that spectrum are fingerprints, specific lines that correspond to elements like hydrogen, oxygen, and helium. These lines appear at known positions, but in distant galaxies, they're shifted, moved, pulled toward the red. By measuring how far these lines have shifted from where they should be, astronomers determine the redshift, and with it, they uncover the galaxy's distance and age.
But redshift is more than just a tool. It's a window into the nature of the universe itself. The discovery of redshift dates back to the early 20th century when astronomer Hubble observed that distant galaxies all appeared to be moving away from us. The farther they were, the faster they seemed to retreat. This wasn't because Earth was at the center of some grand explosion, but because space itself was expanding in all directions. Redshift became the cosmic whisper that told us the universe is growing. And now with instruments like the James Webb Telescope, we can trace that expansion back to its earliest chapters. Galaxies like MoM-z14 serve as markers, ancient beacons from a time when the universe was young, raw, and full of potential. What's astonishing is that redshift also imposes a kind of cosmic limit. Beyond a certain point, galaxies become so redshifted that their light is too faint, too stretched, too hidden in the background noise of the universe to detect. MoM-z14 sits right on that edge, a fragile echo from a realm we're only just beginning to reach. To detect a galaxy at redshift 14 is to push the boundaries of our vision. It's like hearing a whisper from across a canyon that has been widening for billions of years. And that whisper says, "I was here in the beginning." Understanding redshift transforms how we see the universe. It reminds us that every point of light in the night sky is not just distant in space, but in time. The stars and galaxies we see are snapshots from different eras, stitched together into a living portrait of cosmic history. MoM-z14 is one of the earliest entries in that portrait. It represents a time so far removed from us that even light had to fight to survive the journey. And yet, it made it. Across all the stretching, cooling, and expanding of space, it made it.
Chapter 5. How the universe looked when MoM-z14 formed. Imagine a universe without galaxies, without stars, without planets. No glowing suns, no swirling spiral arms, no cosmic fireworks. Just a dark, expanding fog of gas, stretching outward in silence. This was the universe in its earliest days. And this is the setting in which MoM-z14 was born. To understand just how extraordinary this galaxy is, we need to picture what the cosmos looked like around 290 million years after the Big Bang, the estimated time when the light from MoM-z14 began its journey. It was a moment teetering on the edge of transformation, between nothingness and the brilliant birth of structure. The Big Bang itself, some 13.8 billion years ago, had set the universe into motion. In the first few minutes, atoms of hydrogen and helium formed. Then came a long period of darkness. No stars, no galaxies, only cold gas slowly cooling and settling. This was the cosmic dark age, a time when the universe had shape, but no light. It was quiet, but not empty. Tiny fluctuations in density, quantum wrinkles left behind by inflation, had created gravitational seeds in the vast sea of gas. These overdense regions began pulling in matter, slowly growing, collapsing, and heating up under their own weight. Eventually, the very first stars were born. Astronomers call them population 3 stars. They were made almost entirely of hydrogen and helium, untouched by heavier elements. These stars were massive, many hundreds of times the mass of our sun. They lived fast, burned hot, and exploded in brilliant supernova that sent shockwaves across the early universe. It was in the aftermath of these explosions that the first heavy elements, carbon, oxygen, iron, were forged. And it was from this enriched material that new stars and early galaxies began to form. MoM-z14 likely emerged in this chaotic transition from darkness to light. A collection of gas and stars bound together by gravity, surrounded by a halo of invisible dark matter. It may have been small by today's standards, but it was one of the pioneers, a builder in the age of beginnings. The light it emitted, so faint, so ancient, traveled across expanding space, stretched by billions of years of cosmic growth, until it reached us. But what else was happening in the universe at that time? The period when MoM-z14 formed coincides with what astronomers call the epoch of reionization, a dramatic phase in the early universe when ultraviolet light from the first stars and galaxies began to ionize the neutral hydrogen that filled space. In simpler terms, it was a time when the universe began to turn from opaque to transparent. Before this epoch, the neutral hydrogen gas scattered photons, making it difficult for light to travel freely. But as more and more stars ignited, their energy began to clear away the fog, allowing light to pass through the cosmos unimpeded. Galaxies like MoM-z14 didn't just emerge from this transformation, they helped cause it. These ancient galaxies, bursting with new stars, poured energy into the void, slowly carving out transparent bubbles around themselves. Over time, these bubbles grew and connected until the entire universe became visible. This means that MoM-z14 is not just a passenger of cosmic history, it's an agent of change, one of the earliest architects of the visible universe. But the light then would not have looked like it does now. There were no great spiral galaxies, no majestic clusters. The stars were larger, shorter-lived, and more violent. The background temperature of the universe was still several times warmer than it is today. Everything was more compressed, more raw, more uncertain. Imagine a sky lit not by countless stars, but by a handful of intense beacons, massive blue-white giants blazing against a backdrop of endless gas. A place where explosions were common and silence was interrupted by the birth cries of galaxies. It was in this crucible that MoM-z14 emerged, a fragile yet luminous collection of matter glowing in a time before time. Its very presence tells us that galaxy formation began sooner than we once believed, that the universe wasted no time in becoming complex. The discovery of MoM-z14 forces us to adjust our picture of this era. We used to think the first galaxies were small, slow, and disorganized. But here was one, already formed, already shining, barely 290 million years after the universe began. How did it gather enough matter so quickly? How did it ignite so many stars? How did it survive the violence of its environment? These are the questions that keep astronomers awake at night. And perhaps they are questions without final answers. But even without answers, MoM-z14 gives us something profound, a glimpse into a version of the universe we can never see again. A brief, flickering image from a dawn so distant, it almost feels like a dream. And yet it is real. Its light reached us. Its signal was heard. And through it, we remember what the universe once was.
Chapter 6. The Formation of the First Galaxies. Before galaxies stretched across the sky like grand spirals and glowing clusters, before stars danced in brilliant constellations, the universe was quiet, filled with gas, darkness, and potential. It waited. And then, in scattered corners of space, something began to change. The story of the first galaxies is not one of sudden emergence. It is a tale of patience, of gravity's silent work, and of light slowly pushing back the dark. After the Big Bang, the universe was hot and dense, but it expanded and cooled rapidly. In those early moments, only the simplest atoms could form, mostly hydrogen with traces of helium and lithium. Heavier elements didn't exist yet. There were no stars to forge them, no supernova to spread them. What followed was a long, silent age, a time known as the Cosmic Dark Ages. For hundreds of millions of years, the universe was a smooth fog of neutral gas, with only faint quantum imprints left by the earliest fluctuations in energy and density. These fluctuations, though small, were crucial. They were gravity's invitation. The denser regions of gas, barely distinguishable from their surroundings, began to attract more matter. Slowly, imperceptibly, clouds of hydrogen and helium grew heavier, collapsing inward under their own gravitational pull. As they did, they heated up, and deep within those pockets of heat and pressure, the first stars ignited. These were the population 3 stars, the very first generation of stars in the cosmos. They were enormous, many times more massive than our sun, and they burned with unimaginable brightness. But they were also short-lived. Their lifespans were measured in millions of years, not billions. When they died, they exploded in massive supernova, blasting heavier elements into space and disturbing the gas around them. These explosions seeded the universe with the raw materials for the next generation of stars. And in this enriched environment, the first galaxies began to take shape. A galaxy, at its core, is a gravitationally bound system of stars, gas, dust, and dark matter. But in the beginning, they were small, perhaps only 1,000th the size of the Milky Way. These early galaxies were messy, chaotic, and clumpy, lacking the symmetry and order we often associate with more mature systems. They formed rapidly, fed by the cold gas collapsing into dense pockets within vast halos of dark matter, the invisible substance that outweighs ordinary matter by a factor of 5. Dark matter didn't interact with light, but it created the gravitational wells where galaxies could grow. It was the silent architect behind the earliest structures. Many of the first galaxies were likely the result of mergers, small clumps of stars and gas colliding and combining to form larger, more stable systems. These interactions were common, even inevitable, in a universe where everything was closer together. Galaxies didn't grow in isolation. They were shaped by constant encounters, both violent and transformative. Through these collisions, galaxies gained mass. Their stars mixed, their gas was compressed, and new waves of star formation erupted. These early mergers drove much of the rapid growth seen in galaxies like MoM-z14. The galaxy we now observe may be the result of multiple smaller systems coming together in the turbulent dawn of cosmic history. Another essential part of this process was feedback, a term astronomers use to describe how stars and black holes influence their environments. When massive stars explode, or when black holes at the center of galaxies feed on surrounding material, they release energy. This energy heats the gas around them, sometimes halting further star formation, sometimes triggering it. It was a delicate dance between creation and destruction, all orchestrated by gravity, gas, and time. By the time galaxies like MoM-z14 appeared, this process was well underway. It had likely formed stars, merged with neighbors, and contributed to the reionization of the universe. Though tiny by modern standards, it carried the light of progress, the first organized structures emerging from the primordial fog. The formation of the first galaxies also laid the foundation for everything that followed. The elements forged in their stars would one day become planets, oceans, atmospheres, and life. Every carbon atom in your body was once inside a star, born in one of these early galaxies. And so, when we look back and study how galaxies formed, we are also studying ourselves. We come from those stars, from that gas, from those ancient collisions and silent explosions. MoM-z14 is a reminder of that connection, a faint dot in the distant universe, yet filled with meaning. It is part of the great cosmic family tree, a distant ancestor whose light now reaches us, not as a roar, but as a whisper. A whisper that says, "I was here, at the beginning, and so were you."
Chapter 7. Time Travel Through Redshift. Seeing the Past, Not the Present. When you look up at the stars, you're not seeing them as they are. You're seeing them as they were. And the farther away an object is, the older the image becomes. This isn't a poetic metaphor, it's a scientific fact woven into the very fabric of the universe. Light takes time to travel, and the universe is vast. What we observe through our telescopes is not the present. It is a cosmic memory. For MoM-z14, this concept reaches its most extreme form. To understand what we're truly witnessing, we need to talk about redshift. It's the key that allows us to look backward in time. In simple terms, redshift is what happens when the light from a distant object stretches out as it moves away from us. Because the universe is expanding, galaxies are not only moving apart, they're accelerating. As they recede, the light they emit shifts toward longer wavelengths. The distant the galaxy, the greater the redshift. And MoM-z14 has one of the highest redshifts ever recorded. When light shifts to the red end of the spectrum, it tells astronomers that the object is far away, but it also tells them how long ago that light was emitted. In the case of MoM-z14, the light has traveled for more than 13.5 billion years. That means we are seeing the galaxy not as it is today, but as it was shortly after the Big Bang, when the universe was still shrouded in primordial darkness. The deeper we look, the older the universe appears. The James Webb Space Telescope doesn't just take pictures of distant places, it captures images from distant times. With its extraordinary infrared capabilities, it can detect the stretched-out, ancient light from galaxies that formed when the cosmos was still young. It's like opening a photo album that begins with the very first snapshot of existence. But here's the strangest part. MoM-z14, as we see it now, might not even exist anymore. It could have merged with other galaxies, transformed into something entirely different, or simply faded away in the vast timeline of cosmic evolution. What we see is a fossil of light, a silent witness to a long-gone moment in time. To observe MoM-z14 is to peer through a natural time machine. Redshift allows astronomers to map the history of the universe in layers, like geological strata, but made of light. Every galaxy, every star, carries a timestamp embedded in its wavelength. In many ways, we're not just studying astronomy, we're studying time itself. As we continue our journey, keep this in mind. Every faint glow we detect from MoM-z14 carries the signature of a universe not yet fully formed. It's not just the farthest galaxy, it's one of the oldest pieces of cosmic memory we've ever found. A memory floating in the night, still reaching us after eons.
Chapter 8. Cosmic Nursery, MoM-z14 and the Birth of the First Stars. Imagine a time before stars, a time when the universe was dark, silent, and shapeless. That's the world MoM-z14 was born into, a universe still finding its form, still igniting its very first lights. Roughly 300 million years after the Big Bang, the cosmos entered a transformative age. From the murky darkness emerged the first stars, massive, hot, and short-lived. These stars were unlike any we see today. They were composed almost entirely of hydrogen and helium, forged in the primordial aftermath of the universe's violent birth, and they blazed with an intensity that reshaped everything. MoM-z14 likely formed during this era of cosmic awakening. It was not just a galaxy, it was a stellar nursery, a place where the first seeds of light bloomed in a universe that had never seen them before. Astronomers believe that galaxies like MoM-z14 played a crucial role in what's known as the epoch of reionization. This was the period when the fog of neutral hydrogen that filled the universe was slowly cleared away by the radiation from the first stars. It was a cosmic unveiling, a moment when light began to pierce the darkness on a grand scale. MoM-z14, with its early formation and surprising brightness, suggests it housed intense star formation. But how could stars form so quickly and in such numbers in a galaxy so young? The answer may lie in the simplicity of the early universe. Without heavy elements, what astronomers call metals, gas could collapse into stars more efficiently. There were no distractions, no complexities, just pure hydrogen collapsing under gravity's pull. Stars formed rapidly, burning fast and dying young, scattering the first elements into space. These first generations of stars, called population 3 stars, are thought to be enormous, perhaps hundreds of times the mass of our Sun. They didn't live long, but their deaths were spectacular. Their explosions, or supernovae, spread heavier elements like carbon, oxygen, and iron into the void. These elements would become the building blocks of future stars, planets, and even life itself. MoM-z14 may have been one of the first galaxies to host such fireworks, cosmic forges where raw materials were created, scattered, and reborn. In the faint glow we now observe, astronomers are searching for clues, the spectral fingerprints of newborn stars, the telltale signs of supernovae, the signature of creation itself. The galaxy's structure, as seen by James Webb, hints at concentrated pockets of intense energy, regions where stars were likely forming in bursts, lighting up their surroundings and carving space with their radiance. It's humbling to realize that everything we are, every atom in our bodies, owes its existence to these early stars. They were the first alchemists of the universe, turning the simplest elements into the complexity that would one day allow beings like us to look back and wonder. In MoM-z14, we see not only distance, but origin. Not only a faraway galaxy, but a beginning, a spark in the cold. And through this window into deep time, we are reminded, even in the darkest age, the universe was preparing to shine.
Chapter 9. How scientists confirm the distance of MoM-z14. Determining the distance to a galaxy billions of light-years away is one of the most challenging feats in astronomy. Unlike measuring the distance to nearby stars or planets, where methods like parallax work well, galaxies like MoM-z14 push the limits of our tools and techniques. Yet, through a combination of cutting-edge technology and clever physics, scientists have managed to confirm its extraordinary remoteness. The key lies in understanding the galaxy's redshift, a concept we touched on before, but which deserves deeper attention here. When a galaxy is very far away, its light travels an immense distance through an expanding universe. During this journey, the wavelength of the light stretches, moving toward longer, redder wavelengths. This shift can be measured precisely using a tool called a spectrograph. A spectrograph breaks down the galaxy's light into its component colors, producing a spectrum. Within this spectrum are absorption and emission lines, unique signatures of the atoms and molecules in the galaxy. Because these lines occur at specific known wavelengths, their displacement toward the red end tells astronomers exactly how much the light has been stretched and thus how far the galaxy is. For MoM-z14, the James Webb Space Telescope spectrographs were able to detect these lines with remarkable precision. They found a redshift value of about 14. Meaning the light left the galaxy when the universe was only about 290 million years old. But measuring such a high redshift is far from straightforward. The signals are incredibly faint and can be confused with noise or with signals from other sources. Confirming the distance requires careful observation, repeated measurements, and comparison with theoretical models. Moreover, astronomers combine redshift data with photometric measurements, brightness and different wavelengths, to cross-check and reinforce their findings. The galaxy's colors in various infrared filters, along with its spectrum, fit the profile expected for a galaxy at such an extreme distance. This rigorous process of verification helps eliminate false detections or misidentifications. It ensures that what we call MoM-z14 is truly the faint echo of an ancient galaxy, not a closer object masquerading as distant. Confirming MoM-z14's distance also involves ruling out alternative explanations. For example, dust clouds, stars in our own galaxy, or nearer galaxies can sometimes mimic the appearance of distant galaxies in certain observations. Careful analysis helps distinguish between these possibilities. The result? Confidence that MoM-z14 is indeed the farthest galaxy ever reliably detected. This achievement is not just a triumph of instruments like JWST, but also of international collaboration and scientific dedication. Teams of astronomers across the globe work tirelessly to analyze the data, running simulations, and developing new models to interpret what they saw. Every detail matters, from the telescope's precise calibration to the algorithms that separate faint signals from background noise. By confirming the distance of MoM-z14, scientists have opened a new window into the early universe. They have extended our cosmic horizon further than ever before. And in doing so, they have taken us one step closer to understanding how everything began.
Chapter 10: The Role of Dark Matter in Early Galaxy Formation. In the quiet corners of the universe, where visible stars and glowing gas clouds are sparse, there lies an invisible force that shapes everything: dark matter. Though it cannot be seen or touched, dark matter is the unseen architect behind the formation of galaxies, including the distant and ancient MoM-z14. So what exactly is dark matter, and why is it so crucial for galaxies to form in the early universe? Dark matter is a mysterious substance that makes up about 85% of all matter in the cosmos. It does not emit, absorb, or reflect light, making it invisible to all our telescopes. Yet its presence is betrayed by its gravitational influence, pulling on visible matter, bending light, and shaping the large-scale structure of the universe. Without dark matter, the universe as we know it wouldn't exist. After the Big Bang, ordinary matter, hydrogen, helium, and the rest was too diffuse and too hot to collapse quickly under gravity alone. But dark matter, interacting only through gravity, began to clump together much earlier, forming vast halos. These dark matter halos acted as gravitational wells, drawing in ordinary matter. Gas flowed into these halos, cooling and condensing until the first stars could ignite. Galaxies, then, were born inside these invisible cocoons. In the case of MoM-z14, its existence suggests that a significant dark matter halo had already formed less than 300 million years after the Big Bang. This halo would have been the gravitational anchor holding together the gas and stars, allowing the galaxy to grow despite the violent environment of the early universe. Dark matter also influences how galaxies evolve over time. As galaxies collide and merge, their dark matter halos merge as well, shaping the cosmic web, a vast network of filaments and voids that stretches across the universe. Scientists study this cosmic web through observations and simulations, revealing a universe where dark matter forms the backbone and visible matter traces its intricate patterns. Though we still don't know what dark matter is, its effects are undeniable. It's the silent partner in every galaxy's story, including that of MoM-z14. Understanding dark matter helps us understand how the earliest galaxies formed so quickly and why some galaxies survived while others faded away. In this invisible dance between light and shadow, the universe began to sculpt its grandest masterpieces. And through instruments like the James Webb Space Telescope, we are slowly unveiling the secrets hidden in the dark. By confirming the distance of MoM-z14, scientists have opened a new window into the early universe. They have extended our cosmic horizon further than ever before. And in doing so, they have taken us one step closer to understanding how everything began.
Chapter 11: The Significance of Discovering MoM-z14. The discovery of MoM-z14 is more than a mere addition to a list of distant galaxies. It is a profound leap in our understanding of the cosmos, an extraordinary glimpse into the universe's earliest epochs, and a challenge to our most cherished theories. Why is this discovery so important? First, it pushes the boundaries of what we thought possible. Until recently, astronomers believed that galaxies as massive and luminous as MoM-z14 could not have formed so soon after the Big Bang. The universe, they thought, needed more time to cool, to gather matter, to build stars. MoM-z14 defies that timeline. Its very existence suggests that galaxy formation began earlier and proceeded faster than our models predicted. This forces scientists to rethink their assumptions about how the first galaxies grew, how stars formed, and how matter clustered in those first few 100 million years. Second, MoM-z14 is a key piece of the puzzle known as the epoch of reionization. This was a cosmic dawn when the universe shifted from opaque and neutral to transparent and ionized. Understanding which galaxies contributed to this transformation is essential to grasping how the cosmos evolved from darkness into light. By studying MoM-z14, astronomers gain insight into the sources of the powerful radiation that ended the cosmic dark ages. Its star formation rate, luminosity, and structure provide clues about how galaxies like it helped clear the fog that once filled space. Third, MoM-z14's discovery validates the incredible capabilities of the James Webb Space Telescope. It proves that with advanced technology, we can explore deeper, farther, and further back in time than ever before. This opens the door to a new era of cosmic discovery. If MoM-z14 exists, then even older, more distant galaxies might be waiting to be found. Galaxies that formed within the first few 100 million years after the Big Bang, perhaps even earlier. Lastly, MoM-z14 serves as a powerful reminder of humanity's curiosity and determination. It's a testament to our desire to understand our origins, to map the vastness of space and time, and to find our place in the grand cosmic story. Through MoM-z14's faint light, we connect with a universe both ancient and alive, a universe that continues to surprise and inspire. It is a whisper from the past, inviting us to listen closely and to keep looking forward. Chapter 12: Challenges in Observing Such Distant Galaxies. Observing galaxies like MoM-z14 is an extraordinary challenge, testing the limits of human ingenuity and technology. The sheer distances, faintness, and cosmic conditions create obstacles that require patience, precision, and innovation. One of the biggest challenges is simply the faintness of the light. After traveling more than 13.5 billion years, the photons reaching our telescopes are incredibly scarce, mere whispers from the depths of space and time. Capturing them requires telescopes with enormous, sensitive mirrors designed to gather as much light as possible. But collecting light is not enough. The universe is filled with cosmic noise, background radiation, interference from stars and galaxies closer to us, and the thermal glow of the telescope itself. Separating the signal of MoM-z14 from this noise demands careful calibration, data processing, and sometimes repeated observations over many hours or days. Another challenge lies in the redshift of the light. As the light stretches into the infrared,
telescopes must be equipped to detect these longer wavelengths. This is why instruments like the James Webb Space Telescope operate at cryogenic temperatures, far from Earth's warmth, to avoid thermal noise that could drown out faint signals. Moreover, the universe's expansion means that distant galaxies like MoM-z14 can appear distorted or blended with other sources. Astronomers must use sophisticated algorithms and modeling techniques to extract accurate information about their shape, size, and distance. Observing these ancient galaxies also depends on luck, finding them in the right patch of sky at the right time through deep and focused surveys. Every discovery is like finding a needle in a cosmic haystack. Finally, interpreting the data requires theoretical models that can simulate galaxy formation and evolution across billions of years. As new observations challenge existing models, scientists must refine their theories, creating a dynamic dance between observation and explanation. Despite these challenges, the rewards are profound. Each glimpse of a distant galaxy like MoM-z14 is a step closer to unraveling the history of the cosmos, an invitation to witness the universe's earliest moments.
Chapter 13: The Future of Deep Space Observation. As we marvel at discoveries like MoM-z14, it's natural to wonder, what comes next? How will humanity continue to push the boundaries of cosmic exploration and deepen our understanding of the universe's earliest days? The future of deep space observation is bright and filled with promise, driven by a new generation of telescopes, instruments, and technologies. The James Webb Space Telescope has already revolutionized astronomy by opening a window into the universe's distant past. But it is only the beginning. Upcoming missions, such as the Nancy Grace Roman Space Telescope, will survey the sky with unprecedented speed and detail, capturing vast swaths of the cosmos to uncover more faint and distant galaxies. Meanwhile, the extremely large telescope, ELT, under construction in Chile, will feature a giant 39-meter mirror, the largest ever built on Earth. Its incredible sensitivity will allow scientists to study galaxies like MoM-z14 in even greater detail, unraveling their composition, dynamics, and star formation with exquisite precision. Advancements in adaptive optics will sharpen Earth-based telescopes' vision, compensating for atmospheric distortion and bringing distant galaxies into clearer focus. At the same time, new techniques in machine learning and artificial intelligence will help astronomers sift through enormous amounts of data, identifying promising targets and revealing subtle patterns invisible to the human eye. Beyond electromagnetic observations, efforts in gravitational wave astronomy and neutrino detection may someday offer alternative ways to study the universe's infancy, revealing phenomena that light alone cannot show. Together, these developments promise to transform our view of the cosmos, allowing us to peer back farther and with greater clarity than ever before. Every new discovery will challenge our models, refine our theories, and inspire deeper questions about how the universe began and evolved. MoM-z14 is a milestone on this journey, a testament to human curiosity and the relentless drive to explore the unknown. As technology advances, who knows what secrets lie just beyond our reach? The future is waiting, and so are the stars.
Chapter 14: The Importance of Infrared Astronomy. To truly understand the distant universe, astronomers rely on more than visible light. One of the most essential tools in exploring galaxies like MoM-z14 is infrared astronomy, the study of light that lies beyond what our eyes can see. Why infrared? As the universe expands, the light emitted by ancient stars and galaxies stretches and shifts from visible wavelengths into the infrared. This phenomenon, called redshift, means that the earliest galaxies glow most strongly in infrared light. Detecting this infrared light requires special instruments and conditions. Ground-based telescopes face a major challenge. Earth's atmosphere absorbs much of the infrared spectrum, and our planet's warmth creates a background glow that drowns out faint signals from space. That's why space telescopes, like the James Webb Space Telescope, are placed far from Earth, cooled to near absolute zero to reduce thermal noise. Infrared astronomy allows us to peer through cosmic dust clouds that obscure many regions in visible light. It reveals star-forming nurseries, the centers of galaxies, and the faint glimmers of ancient galaxies billions of light-years away. For MoM-z14, infrared observations were crucial. Its light, stretched deep into the infrared, would have been invisible without Webb's specialized instruments. Infrared astronomy opens a window into epochs and regions of the universe hidden from visible light. It tells stories of star birth, galaxy evolution, and cosmic history written in the heat of the early universe. As technology advances, infrared astronomy will continue to be at the forefront of discovery, helping us unlock the mysteries of galaxies like MoM-z14 and beyond.
Chapter 15. The Mystery of Cosmic Dawn. Cosmic dawn, the moment when the first stars and galaxies lit up the universe, is one of the most profound mysteries in astronomy. It marks the end of the cosmic dark ages and the beginning of a universe filled with light and structure. MoM-z14 shines as a beacon from this mysterious era, offering clues to a time when the cosmos was waking up. Despite advances, many questions remain unanswered. How did the very first stars ignite? What triggered the rapid formation of galaxies like MoM-z14? How did these early lights transform the surrounding universe? Astronomers seek to understand the timing, pace, and processes of this cosmic awakening. Was it a slow, gradual illumination or a sudden burst of light? Did all regions of space light up simultaneously, or did pockets of brightness spread like wildfires? Observations of galaxies like MoM-z14 help piece together this cosmic puzzle. Each new discovery adds detail to the picture of cosmic dawn, revealing a universe alive with energy, transformation, and creation. Yet the full story remains elusive, waiting to be uncovered by future telescopes, new theories, and deeper exploration. Cosmic dawn reminds us that the universe is dynamic, ever-changing, and full of surprises. MoM-z14 is not just a distant galaxy, it's a messenger from that awakening, carrying whispers of light across billions of years. Listening to its story, we connect with the origins of everything we see today.
Chapter 16. How MoM-z14 changes our understanding of galaxy formation. Before MoM-z14's discovery, astronomers had a framework for how galaxies formed, gradually, over hundreds of millions of years, starting from small clumps of gas and dark matter. But MoM-z14 challenges that narrative, suggesting a faster, more complex process. This galaxy shows us that massive, luminous galaxies could have existed much earlier than previously thought, forming just 290 million years after the Big Bang. Such rapid assembly requires reconsidering how matter clumped together, how quickly stars ignited, and how galaxies evolved. Perhaps early galaxies formed through intense bursts of star formation, fueled by abundant cold gas and efficient cooling processes. Maybe the dark matter halos that cradled these galaxies were larger or denser than models assumed, speeding up gravitational collapse. MoM-z14's existence pushes scientists to refine simulations and rethink the physics of the early universe. It highlights the need to explore the role of feedback mechanisms, mergers, and the interplay between stars and their environment in shaping young galaxies. Ultimately, MoM-z14 is a beacon, showing that the universe was more dynamic and diverse in its youth than we imagined. It urges us to keep searching, questioning, and revising our understanding. In this ever-evolving cosmic story, each discovery rewrites the chapters before, guiding us closer to the truth of our origins.
Chapter 17. The technology behind discovering MoM-z14. Discovering a galaxy as distant as MoM-z14 required the pinnacle of modern technology, a marvel of engineering and innovation designed to peer across billions of years of cosmic history. At the heart of this discovery is the James Webb Space Telescope, JWST, the most powerful space telescope ever built. Launched into orbit beyond Earth's atmosphere, Webb escapes the limitations of ground-based observatories, such as atmospheric distortion and infrared absorption. Webb's massive primary mirror, composed of 18 hexagonal segments, spans over 6 meters in diameter. This giant eye gathers faint light from the farthest reaches of the universe, focusing it onto advanced instruments capable of detecting the faintest infrared signals. Its near-infrared camera, NIRCam, and near-infrared spectrograph, NIR-SPEC, were crucial for identifying MoM-z14's signature. NIRCam captures detailed images in the infrared, while NIR-SPEC analyzes the spectrum, revealing the galaxy's composition, redshift, and distance. Operating at cryogenic temperatures near -266 degrees Celsius, JWST minimizes its own heat emissions, allowing it to detect the universe's faintest infrared glimmers without interference. Behind the scenes, powerful data processing and sophisticated algorithms filter noise, enhance signals, and interpret complex data, turning raw measurements into meaningful discoveries. International collaboration among space agencies, universities, and research institutions ensured JWST's success, from its design and launch to its ongoing operation. The discovery of MoM-z14 showcases not just a distant galaxy, but the remarkable achievements of human curiosity, cooperation, and technology. Through this lens, we glimpse the universe's earliest light and step closer to answering timeless questions about our cosmic origins. Chapter 18. What MoM-z14 tells us about star formation in the early universe. MoM-z14 is not just a record-breaking dot in the sky. It is a window into a time when the universe was still forming its first stars. The light we receive from this galaxy comes from a moment roughly 290 million years after the Big Bang, when the cosmic stage was still young and chaotic. One of the most remarkable revelations from MoM-z14 is how quickly stars began to form after the universe's birth. Scientists once believed that it took hundreds of millions of years for the first stars to ignite. But MoM-z14 suggests that galaxies like it were already teeming with starlight far earlier than we expected. This raises a deeper question. How did stars form so rapidly in such an immature universe? In the early cosmos, hydrogen gas dominated. In dense regions, gravity compressed this gas into clouds, which then collapsed under their own weight, igniting nuclear fusion in the hearts of newborn stars. What surprises astronomers about MoM-z14 is the efficiency of this process. It implies that the conditions for star formation were present and active in a shockingly short cosmic timespan. The spectral fingerprint of MoM-z14 shows evidence of young, hot, massive stars, those that burn bright and fast. These first-generation stars are likely different from the stars we see today. They were born in a universe without heavier elements, making them more massive and more intense. Their explosive deaths seeded the universe with the first atoms of carbon, oxygen, and iron, the building blocks for future stars, planets, and eventually life. MoM-z14 also helps refine our understanding of reionization,
the era when light from early galaxies began to clear the fog of neutral hydrogen that filled the universe. Star formation in galaxies like MoM-z14 played a key role in this transformation, turning a dark universe into a transparent one. The data from MoM-z14 reinforces a powerful idea. The universe wasted no time creating light. It was eager to shine, and galaxies like this one were at the forefront of that cosmic dawn. By studying MoM-z14, astronomers are not just learning about one galaxy, they're peering into the collective story of all galaxies, including our own Milky Way, and the mysterious forces that sculpted them. In the silence of deep space, MoM-z14 whispers ancient secrets about how the universe found its spark.
Chapter 19: The Redshift Mystery and the Light from MoM-z14. Light travels. It journeys across the cosmos at nearly 300,000 kilometers per second, carrying with it stories from long ago. When we observe distant galaxies like MoM-z14, we're not just seeing something far away, we're seeing something ancient. The redshift of its light tells us exactly how ancient. MoM-z14 holds the record for the highest confirmed redshift, clocking in at a redshift of z equals 14.32. But what does this number really mean? Redshift occurs when light stretches as it travels through the expanding universe. The greater the redshift, the farther the object, and the older the light. At z equals 14.32, the photons we detect from MoM-z14 began their journey just 290 million years after the Big Bang. That's over 13.3 billion years of uninterrupted travel, moving through expanding space, bending under the influence of gravity, slipping between galaxies and stars, before finally reaching our telescopes. But redshift is more than a measure of distance. It's a cosmic fingerprint, revealing clues about the temperature, speed, and even composition of the light's source. The spectrum from MoM-z14 contains signatures of ionized hydrogen and young stars, allowing scientists to reconstruct the environment from which this light originated. One of the most captivating aspects of MoM-z14's redshift is how it challenges our models. Before this discovery, the most distant known galaxies were around redshift 13 or below. Pushing into z equals 14 territory means that galaxies were forming and shining earlier than predicted. The universe was evolving rapidly, more rapidly than our simulations had anticipated. And so each wavelength of stretched light from MoM-z14 becomes a piece of the puzzle, pushing astronomers to revisit the assumptions they've made about cosmic timelines. We often imagine the early universe as a featureless void, but the redshift from MoM-z14 tells another story. It was already alive with movement, light, and structure. Hydrogen clouds were collapsing, stars were forming. Galaxies were assembling into the first islands of matter in an ocean of darkness. The mystery deepens when we realize this light is not just stretched, it is distorted, subtly altered by the fabric of space and time. As it travels through gravitational wells or interacts with other cosmic phenomena, it carries imprints of those encounters. That means the light from MoM-z14 is more than just a message from the past. It's a chronicle of the journey itself. To detect such faint light requires extraordinary instruments. The James Webb Telescope, with its infrared sensitivity, is uniquely capable of catching these ancient whispers. Without it, MoM-z14 would remain hidden, its message lost in the noise of the universe. But now, that light is here, faint, redshifted, and ancient. And in it, we see not only a distant galaxy, but a moment when the universe was waking up, learning to shine, to expand, and to evolve. MoM-z14's redshift is a number, yes, but it is also a threshold, a door to deeper cosmic truths. One photon at a time, the universe gives up its secrets. Chapter 20:
The edge of vision. What comes after MoM-z14? Standing at the frontier of the known cosmos, we gaze at MoM-z14 as if it's the final lighthouse before darkness. Its light, born in a time when the universe was less than 2% of its current age, seems to mark the edge of visibility. But is it truly the edge? The universe is vast, not just in space, but in time. And every time we redefine the limits of what we can observe, we uncover more questions than answers. MoM-z14 is not a finish line, it's a starting point. Already, astronomers speculate that galaxies formed even earlier, perhaps at redshifts of 16 or 17. These would represent the first true sparks after the cosmic dawn. Collections of stars so young, so hot, and so brief in their lifespans that they may have vanished long before they left behind elements heavier than helium. But if they existed, why haven't we seen them? The answer lies not just in technology, but in cosmic opacity. For hundreds of millions of years after the Big Bang, the universe was veiled in neutral hydrogen, absorbing most of the ultraviolet light from young stars. It wasn't until the epoch of reionization, a cosmic phase transition, that the fog began to lift. Galaxies like MoM-z14 were likely agents in this transformation, their energy breaking apart hydrogen atoms, turning the opaque cosmos into the transparent one we know today. MoM-z14 may represent one of the galaxies responsible for reionizing the universe, but what lies beyond it, before that process fully began, remains largely hidden. And yet, scientists are reaching. With the Webb telescope's successors already on the drawing board, humanity is building the tools to see the unseen. Missions like the Nancy Grace Roman Space Telescope and future ground-based observatories like the Extremely Large Telescope, or ELT, are being designed to push even deeper, to seek the first light. Theoretically, we could glimpse population 3 stars, the first ever formed, gigantic, unstable, and composed only of hydrogen and helium. These stars were the cosmic forges that created the first heavier elements. They lived fast, burned bright, and died in spectacular supernovae that seeded the cosmos for everything that followed, including us. Imagine detecting the remnants of these titanic deaths, preserved in ancient galaxies whose light is still drifting towards us. Imagine discovering proto-galaxies, collections of gas and dust just beginning to clump together, not yet shining, not yet forming stars, but harboring the seeds of entire galaxies. Even MoM-z14 might not be alone at the edge. There could be others, dimmer, smaller, more distant, just beyond the threshold of our vision. Each future detection will peel back another layer of time, another chapter of the universe's autobiography. But beyond a certain point, light itself becomes useless. The cosmic microwave background, at 13.8 billion years old, is the final flash of visible evidence from the Big Bang. Anything before that belongs to the opaque era, where particles danced in darkness. To understand that realm, we'll need not telescopes, but instruments that detect gravitational waves, neutrinos, or other messengers not bound by light. And so, even as we marvel at MoM-z14, we must remember, this is not the end. It's just the beginning of the beginning. The redshift may increase, the light may fade, but our curiosity will not. With each photon we collect, we push farther into the darkness. And the universe, it continues to whisper, waiting for us to learn how to listen.